Hello everyone and welcome. My name is Zahidul Islam and I'm from the Water and Waste Policy Branch of Alberta Environment and Parks. Today, I'm going to talk about evaporation and evapotranspiration in Alberta based on 5 evapotranspiration models. Before I start, I want to recognize the contribution of the co-authors of this study, Dr. Shalini Kashyap and Mr. Michael Seneka from Alberta Environment and Parks. Evaporation is the process whereby liquid water is converted to water vapor and removed from the evaporating surface. For example, lakes, rivers, pavements, soils, and wet vegetation. Transpiration is the process of water loss from plants through small openings found on the underside of leaves, namely stomata. The collective term evapotranspiration is the loss of water from the water surface through the combined process of evaporation and plant transpiration. In Alberta, provincially averaged annual precipitation is about 502 mm, while the average runoff is only about 98 mm, and the average annual groundwater recharge is about 41 mm. Therefore, the average annual evapotranspiration is about 373 mm, which is about 74% of its total precipitation. So, proper estimation of evapotranspiration is essential in water balance calculations in Alberta. This is a snapshot of different types of evaporative loss in Alberta in a long-term averaged monthly scale. This plot is based on Morton's evapotranspiration model run by 65 years of data in 19 locations in Alberta. 4 bar charts showing median values of 4 types of evaporation: gray for potential evaporation, green for potential evapotranspiration, blue for shallow lake evaporation, and orange for actual evapotranspiration. The error bar showing the range of evaporative loss. As you noticed, evaporative losses are very low in winter months. In winter months, it is often possible to obtain negative values for evapotranspirations in Alberta. However, it is important to investigate whether these negative evaporative losses are also common in other evaporation models. There are 3 core objectives of this study. Number 1, estimate monthly potential and actual evapotranspiration from various models at different locations in Alberta. Number 2, compare long-term averaged monthly potential and actual evapotranspirations from different models. And finally, analyze the potential and actual evapotranspiration for winter months to investigate the issue of negative evaporative loss. We used 4 evapotranspiration models to compare potential evapotranspiration. The models are the Hammond, Penman, Penman-Monteith, and Morton's. And then we used 2 evapotranspiration models to compare the actual evapotranspiration, and those are the Morton and Granger-Gray. This slide shows the locations of the climate data. We used Alberta Agriculture and Forestry graded historical climate data in our analysis. We adopted a simple methodology to compare various models. First, we ran the selected evapotranspiration models using the 65 years of daily climate data for 19 locations in Alberta. Then, we aggregated the simulated potential and actual evapotranspiration in long-term averaged monthly values. Finally, we compared the long-term averaged potential and actual evapotranspiration in annual and monthly scale as well as for the winter months. In this plot, we are showing the comparison of long-term averaged monthly median potential evapotranspiration in Alberta simulated by 4 models: the Hammond, Penman, Penman-Monteith, and Morton. The error bar shows ranges of potential evapotranspiration from the medium values. We found that, with the exception of the Hammond method, all potential evapotranspiration models could predict negative numbers during the winter months. While the Morton's method gives a greater variability for monthly median values, it is somewhat more complex and requires more input data compared to the other methods and has the potential for application under greater condition compared to the other equations. This plot shows the comparison of long-term averaged monthly median values of actual evapotranspiration in Alberta simulated by two models, the Morton and Granger-Gray. The error bar shows ranges of actual evapotranspiration from median values. Here, we again observe the Morton's method shows greater variability in median monthly values. Scientists have reported both these equations successful for estimating water balance. In this plot, we compared long-term averaged January and December median potential evapotranspiration at 19 locations in Alberta, simulated by four models, the Hammond, Penman, Penman-Monteith, and the Morton. We observed Morton's model consistently provides negative potential evapotranspiration values for January and February in most of the locations except Lethbridge and Vauxhall. January and December potential evapotranspiration can be as low as -5 mm and -6 mm respectively. The Penman-Monteith model does not provide any negative potential evapotranspiration for any of those stations for January. However, December potential evapotranspirations at Calgary and High Level was slightly negative. The Penman model does not provide any negative potential evapotranspiration for any of the stations in January. However, for some stations, December potential evapotranspiration values were estimated as negative. Hammond method does not provide any negative potential evapotranspiration. In this plot, we compared long-term averaged January and December median actual evapotranspiration at 19 locations in Alberta, simulated by two models, the Morton and Granger-Gray. We observed Morton's model consistently provides negative actual evapotranspiration values for January and December in most of the locations except Lethbridge. January and December actual evapotranspiration can be as low as -5 mm and -6 mm respectively. The Granger-Gray method estimated negative actual evapotranspiration values for 80 stations in January and 13 stations in December. Since the Morton model consistently provides negative actual and potential evapotranspiration for January and December months, we further investigate the model equations to see what is causing such values. The plot on the left shows monthly net radiation versus air temperature, and the plot on the right shows net shortwave and net longwave radiation in Alberta. All of these plots are based on 65 years of data. We observed during winter months, when air temperature becomes negative, net radiation also becomes negative. The average net long-wave radiation and short-wave radiation for December to January months, estimated for 65 years of period, ranges from 54 to 65 watt per meter square and 3 to 33 watt per meter square, respectively. It is inferred that during winter months, especially in January and December, the net long-wave radiation offsets the net short-wave radiation and results in negative net radiative energy. Based on our study, we conclude that Penman and Penman-Monteith often provide negative potential evapotranspiration at some locations during December and January. Granger-Gray methods provide negative actual evapotranspiration at various locations in Alberta, especially in January and December. Negative potential evapotranspiration and actual evapotranspiration values are more evident in Morton's model compared to other models. And application of these models to analyze the water balance for a watershed may be necessary to understand the implication of such negative evaporative losses. Thanks for watching. Although it's a virtual conference and this presentation is recorded for viewing, I will be present in the Q&A session on May 28, 2021 at 1 to 1:30 p.m. Eastern Time. I would be happy to answer any questions and listen if you have any comments. Also, please feel free to send us an email. Thanks and goodbye. See you on May 28th.